so let's look at another example involving induction. We're going to look at something a little bit different. Prove that for every integer n greater than or equal to 5, 2 to the n is greater than n squared. So this is a little bit different than anything we've looked at before, number one, because it involves an inequality, but also because we're looking at the smallest n could be is 5. And so what that does is that changes our basis step in our proof. So we're going to write our outline of our proof, right? And the first part is the basis step, which in this case is going to be n equals 5. If I look at n equals 5, the question is 2 to the 5th greater than 5 squared? Well, 2 to the 5th is 32. 5 squared is 25, so this inequality is true, which means we've done the basis step. So now let's look at the inductive step. You're going to assume that it's true for some positive integer k that's at least greater than or equal to 5. And then in the end, we're going to remind ourselves, right, at the end of this, what do I need to show? So in the end, I need to show that it's true for k plus 1, that 2k plus 1 is greater than k plus 1 squared. Okay, so keep that in mind. I'm going to start with this left-hand side. So we have 2 to the k plus 1. That's 2 times 2 to the k. And so now I have 2 to the k, which I know is greater than k squared. So this is greater than 2 times k squared. And so in the end, right, I need to show that this thing is greater than k plus 1 squared. That's what I'm trying to work to. And so we'll say we need to show that 2k squared, because I already have this greater than symbol here, I just need to show that it's greater than or equal to k plus 1 squared. Well, what does this really mean? This means that 2k squared is greater than or equal to k squared plus 2k plus 1 if we FOIL out the right-hand side. So now let's look. I have 2k squared. That's the same thing as k squared plus k squared. Another way you can view that is it's k squared plus k times k. And remember that k is at least 5. So I'm going to substitute in for this k. This is greater than or equal to k squared plus 5k. That's because, so I'll say since k is at least 5, so now let's see, what do I got? I can split up this. If you look at what you're trying to go to, right, we're trying to show this is true. Look at my coefficient on k, it's a 2. So I can break this up k squared plus 5k as k squared plus 2k plus 3k. And remember, k is at least 5. So what's this last term? It's at least 15. Since k is at least 5. And what that means is that's going to be strictly bigger than k squared plus 2k plus 1, which is what we needed to show. All right, so let's write up this proof formally now. So, all right, proof. So I'll say we proceed by induction for n equals 5. 2 to the 5th is bigger than 5 squared is true since 32 is greater than 25. Now, assume 2 to the k is greater than k squared for some positive integer k is greater than or equal to 5. Now, we had 2 to the k plus 1 is 2 times 2 to the k, which is greater than 2k squared. Since k is at least 5, we were able to show that 2 to the k plus 1 is greater than k squared plus k squared, which equals k squared plus k times k, which is greater than or equal to k squared plus 5k. We have that 2k plus 1 is greater than k squared plus 5, which is k squared plus 2k plus 3k, which is greater than or equal to k squared plus 2k plus 15. That's because k is greater than or equal to 5. Finally, we have that 2 to the k plus 1, it's greater than k squared plus 2k plus 15, which is strictly bigger than k squared plus 2k plus 1, which equals k plus 1 squared. Therefore, 2 to the k plus 1 is greater than k plus 1 squared. And that's the end of our proof.